The last video we talked about interference with two sound sources of the same frequency. Let's look at interference due to two sound sources with different but close frequencies, and we're going to get into this idea of a beat. So let's look at a demonstration first. Here we have two sine waves. One is at 500 hertz. This is the first wave here. The second wave is at 600 or 550 hertz. And when you do a addition between each of the waves, if I were to draw a vertical line straight through and do addition, this would be the result of the addition down here in the y graph. So it's just the summation every time t, whatever value that is. Now, as I start the simulation, you can see the dots moving along the different sine waves. You can see how they go out of sync, and the black dot then represents how those differences start to appear, and this is called a pulse. You notice that the resulting wave comes in these packets. There's still a sine and a cosine inside the packet, but you get this envelope, these pulses. Now you would actually hear these pulses occur if you had two speakers that had slightly different frequencies. You would actually be able to hear this pulse, and it would sound kind of strange. I hope I can bring my guitar in and show you this. So now let's take a look at the mathematics behind pulses. So let's start with our first function, and we're just going to look at it in terms of time. We're just going to assume that we're in the same location, so x is equal to 0. So we'll have our first function, d1, is equal to some amplitude times sine of 2 pi frequency 1 times time. And we'll have function d2, our wave d2, will be same amplitude, sine of 2 pi frequency 2 times t. Now our total wave is just the addition of the two, and I can distribute the a out for the amplitude, and I will get sine of 2 pi frequency 1 times t plus sine of 2 pi frequency 2 times t. Now, I kind of seem to be at a standstill. I have a summation of two sines. Doesn't seem like I would be able to get any more information out of this, but let's use an identity. So we have sine of theta 1 plus the sine of theta 2 is equal to 2 sine theta 1 plus theta 2 over 2 times the cosine of theta 1 minus theta 2 over 2. And now I can put these signs into this identity and simplify, and I get d is equal to 2a times cosine 2 pi times f1 minus f2 over 2 and then I'm going to have sine 2 pi frequency 1 plus frequency 2 over 2, and I forgot my t over here in the cosine. And now you see you have a sine wave, but now you have a cosine that gets attached to this amplitude. And this is what makes your envelope. This is what makes the top and bottom piece where the wave is in between. So the sine part is inside, the cosine is the outer part. So the beat frequency is just equal to the absolute value of f1 minus f2. Well, why is it the absolute value? Well, we only hear the beats and we hear a tone, but we can't tell if f1 is greater than f2 or if f2 is greater than f1. It's indistinguishable. We can't make that assumption. So something in the problem will have to tell us whether we use f2 minus f1 or f1 minus f2. We don't know. We'll have to tell that from the problem. We just know that all we can hear is the beat. So beat frequencies are real. They can be used in different applications, and you'll actually have a homework problem, actually an exam problem, that will use beat frequency and our next topic, Doppler, together, and coming up with a solution to the problem.